Let's start. I have some comments on the exercises. All the exercises are on the web already, and they're quite large, so you should have sort of enough to do. So you don't necessarily need to solve all the problems, but try to solve the ones that are hard, because that's probably the ones you need to work on. And they're quite mathematical in nature. So the exam problems will probably be easier in the sense that there will be less calculations to do, because there's limited time on the exam. But I think they should be an okay practice to work on to get to understand the physics. And then I think you need to do calculations. Also, we have a guest here today with a camera. Yeah, hi. So we're trying to put the lectures on iTunes for this course. So if you're hungover or late or something, you could watch the lectures on iTunes after a couple of days, I think. So we'll see how that goes. Now let's get back to the image method. So last week we solved this problem. We have a point charge that's hanging in the air above a metal conductor. The distance is d. And now we solved for the potential V in this region up here by transforming this into an image problem, which gives the same solution in this region. But of course it looks completely different. It's only 2-point charges. And because we got them on this form of only 2-point charges, we could just write down the solution. It was very easy. So today I'm going to show you that as soon as we have this solution, we could find the charge density by looking at the boundary conditions. So I'm just going to write down the boundary condition on this surface right here. So the difference in the vertical component of the D field is proportional to the, well, it's equal to the charge, surface charge density. But now, of course, this is only the set component. And for set larger than 0, we have a vacuum. So it's so this is very easy. The displacement field is just proportional to the electric field with a constant epsilon 0. And inside the metal, the field is of course 0. So I can just take away this term. And now I know, of course, that the set component of the electrical field, this is the set derivative of the potential. Like this. So now I can just calculate the charge density on this metal surface by just taking the set derivative of the potential. And the answer is pretty straightforward. So it's set minus d over the distance from the top charge. And it's set plus d minus divided by the distance cube from the bottom charge. So now, of course, this is the set component of the electrical field. Oh, this is the set component of the electrical field in the whole region. But now, of course, I'm interested in the set component at the surface. So I'll just set equal to 0. And then we'll get the charge density right out. Like this, and now you see there's a factor 2 because these two terms become equal. Well, if I did the signs right, but I don't think I did. Okay, so that's it, and now, as you can see, we have a positive charge Q on the top, this point charge here, and it induces a negative charge density, or the opposite sign charge density on the metal surface. So if you go far away, it's going to look neutral in the net effect. And this is, of course, because the metal can just supply an infinite amount of charge because it's an infinitely large slab of metal. So it's got charges somewhere. And now, of course, you could wonder what's the total charge that's been induced on the surface. And we can just solve that by integration. So I'll call it Qi for induced. And I'll integrate this over the whole surface. And to no surprise, the answer is minus Q. So as you can see, by just solving the Laplace equation, and then you can use the boundary condition to find the charge density, we see that the induced charge density, the total induced charge on the surface on the metal, is equal to the charge in the vacuum. Okay, and also there was a question last time about the electrical field, and of course it's the same in the two problems, but it's not the same in this region, because in the metal it has to be 0. So we find the potential for this system, then we go back here, and then we find the electrical field on the upper side. And this is important because then the total stored energy is proportional to the electric field square. So because the electric field is more or less the same with a minus sign on the different sides, so the energy stored would be twice the amount in the real problem, because the space is twice as large. So it's important to go back to the original problem once to find the potential. Okay, so now we're going to have a brief look at a different example, which is a point charge near a grounded sphere. So there's a grounded metal sphere here, or at least a conducting sphere, and there's a point charge here in a distance A. I'll try to make a bigger one, I think. And now, because of the rotational symmetry around this x-axis, I'm going to put the image charge somewhere here. And of course, remember that we have to put the image charge inside the sphere, because we can't put charges in our original domain. We have to put it outside the domain we're interested in. So I have to put it inside the sphere. And I'll call this distance b, and this is, of course, the origin. Okay, and now you can just write down the potential like last time. So it's essentially Q over the distance from the point charge outside our the original point charge. And there's a different charge, q bar, here. And note that q bar is not equal to q. And we're going to show this. So that's what it looks like. And now, I think maybe you should do this as a home exercise to check that the calculation I'm about to do gives the right answer gives the right answer everywhere. But I'm just going to do the following trick. I'm going to assume that it all works and that the potential then has to be 0 here and here, because then I have an equation only in x, right? So now, of course, these terms look, these factors here look like this. And now if I can take away the y and the z, then the whole problem is much easier. So if I, let's see, x equal to r, so like this, I put y and z equal to 0 and x equal to r. So it's this point here. And of course the potential should be 0. And if I write out that 0, it turns into, well, what is it? Over here you see x minus d. So this should be equal to 0. And now we find one equation for the two unknowns, which are, no, sorry, it's not d anymore. It's a. So it's a and b, like this. And now we get one equation for two unknowns, which are q bar and b. Because I don't know how large the image charge is, and I don't really know where to put it. I only put it on this axis because of the symmetry, it has to be there. But I don't know exactly where to put it, and I don't know how big it should be. So now this is one equation, and I can find another equation by looking at this point here, which is then at x equals minus r. And I think I'll leave it as a homework exercise for you to figure out these equations, so we can continue on separation of variables today. Okay? So are there any questions to this stuff? The potential has to be 0 here because I say that this metal sphere I connected to a ground somewhere with a wire that doesn't matter. I'm just saying that the potential has to be 0 on this metal sphere because there can't be any electrical fields inside. So I just set the potential to a constant, and 0 is a great constant. And then on the surface, the potential has to be constant then. And that's this point here. Was that a good answer? Okay?
And how do you know that this works everywhere else except for the x-axis?
I don't know that it works.
Okay.
Well, you can show it. And that's going to be your homework as well. So you figure out, you could just pick one point in this plane, right? Because you have rotational symmetry. And then show that the potential is 0 for when you find the values for q bar and b. And the solution is in the textbook. So you can check that you're doing it right. Was that a good answer? Okay. And also, it's not clear from the beginning whether this method is going to work at all. Usually it requires some form of symmetry. For example, if you have a cube, there's no way you can do it for a single point charge. And there's no way to know except try, I guess. Also, some people do computer simulations by putting a lot of small image charges everywhere to sort of approximately match the boundary conditions. Okay, so we're now going to discuss one of the direct ways of solving the Laplace equation, and it's called separation of variables. And it's chapter 3.2 in the book. So the idea is to write the potential V as a product of functions in the various coordinates. So there's one function for each coordinate, depending only on that coordinate. So we're going to start out with just a classical example, which is Cartesian coordinates. And we write the solution to the Laplace equation like this. This is just in general. So some function big X or only X, big Y of only Y, and big Z of only Z. So now we try to solve this Laplace equation by assuming this form of the solution, which might not be the case, but we're going to try anyway. And then we try to find an ordinary differential equation for each coordinate. And now I'm going to do an example which looks like this. Sorry, my brain and the notes are not in agreement. Okay, so now I put a metal plate at y equals 0. So this is a huge metal plate which stretches into infinity starting from x equals 0. And there's also a metal plate at y equals a. So there are two metal plates, and they're starting at x equals 0 and stretching out into infinity. And I'm going to put v equals 0 on both of these plates, like this. And now at x equals 0, I also put a plate, but at a different potential. which are called V naught of y. So let's just write down the boundary conditions for this. And now we all agree that that BC stands for boundary condition, so I don't have to write that all the time. Let's see. First of all, at this bottom plate, the potential has to be 0. Second of all, it has to be 0 on the other plate at y equals a. Third, if I run off to infinity, let's say if I go to large x, I shouldn't see much of this stuff here, so the potential should go to 0 as I approach infinity. Like this. And let's see, that's the fourth one actually. Again, the brain is not in agreement with the notes. And then, and now of course I can't put the potential 0 everywhere because it would be very, very boring. So I'm going to put this function here. This function here is not going to be just 0. And I'm calling it V naught of y. So that's the problem. And also I note, of course, that the set dependence doesn't exist because there's translational symmetry in this direction. So there's no set derivative of the potential. So the problem is to solve this equation. Under these boundary conditions. And this is a sketch of the system. Does everyone understand the geometry? And by the way, if you ask a question, the microphone doesn't hear it, so you're not going to be put on iTunes, if you're worried about that. No one? Okay. So now I'm going to start off by just assuming a solution that looks like this. So u is a function only of x, and w is a function only of y. And the potential is just a product of the two. So let's see. I'm denoting the Laplace equation by star. So inserting into star. I get the following. Like this, and now I can divide by u times w, or the potential itself. And in that way, I'm going to just get a function of u here and w here. And now, of course, as this is only a function of x, and this is only a function of y, and the sum of them should be equal to 0, well, they must each be equal to some constant. Otherwise, this won't add up for all x and all y. So now I'm going to say that the first term one of u dxx u is equal to c is equal to minus the second term I just move it on the other side and say that they have to be equal to a constant. And that's this. And now in general we have to check the following three different possibilities. C could be equal to 0 because that would satisfy this equation. And it could be less than 0 and bigger than 0. But of course I cheated, so we know that the following is the correct. And that's this one here, of course. Let's see. So now I have two ordinary differential equations, and they look like the following. Oh yes, and because this is positive, I'm just going to set c equal to k squared, because then if k is a real number, then we know that c is going to be positive. So I just put that into it. So the second derivative of the u function is equal to a constant, which is positive, times the function itself. And same for the w function, except there's an opposite sign. And now you all remember the solution, so I don't have to do any calculations. And that's of course just a sum of exponentials for the x function. And for the y function, it's going to be a sum of sine and cosine functions. Like this. And now I know what the solution is going to look like. It's going to be a product of two exponentials and two sine cosine functions. So now I have to just figure out what's a, b, c, and d, and the k. And then I'm going to be, and then I'll be done. So I'm going to start out in a logical order, starting at the last boundary condition. Number 4. And it says that as x tends to infinity, the potential should go to 0. And now if you have a look over there, I can't even see it, but I guess it's a e to kx, that term has got to be 0, right? Because otherwise it's going to blow up at infinity. So I'm setting a equals 0. And that reduces the whole thing a bit. So the potential now looks like this. So it's an exponential which makes sure that the whole thing decays as we go to large x, and these oscillating terms which we'll have to sort out with some other boundary conditions. So let's see, let's move on. Yeah, so I had a B. The question is what happened to B? And I'm now saying that this is just an arbitrary C and a D. So maybe if you let me do this, I'll just put a prime on those. And now the new C and the new D are different, right? So these are arbitrary constants which we have yet to determine. And because of that, I could just say that this is a new C and this is a new D. And now because I have one on each term, I don't need one in front of here. Is that okay?
Yes.
Great. So now, let's look at the first boundary condition, that the potential should be 0 at y equals 0. So so that's the boundary condition. And well, you all know that cosine of 0 is 1. So that means that I'm going to be stuck with D at 0. So we have to have D equals to 0 to make sure that the potential is always 0. Okay? And now the potential is even simpler. Like this, and there's only one constant, an arbitrary constant, and this k to determine. And let's look at the second boundary condition. And it says that we have the same thing as here, except that y equals a. Like this. And to do that, we have to modify the k so that the sign just has time to go one wavelength, or a half a wavelength, or an integer number of half wavelength, so that we end up at 0 again in the sine function. Because then we'll have that v is equal to 0 at this plane for, well, for any values of c. And this we can do in the following way. Let's see. Yes. Like this. So now when y is equal to a, then k times y is equal to an integer number of half wavelength. So in that way, the sine function is going to make sure that here is going to make sure that the potential is 0 on the other plane as well. But this now, because we have, let's see, n is of course an integer. So n is equal to 1, 2, 3, and so on. And now we have an infinite number of solutions which could possibly satisfy the boundary conditions. So I can write the solution in the following way. So I call this solution now Vn, because there's one solution for each positive n. And the total solution could be any linear combination of those, because the nabla square is linear. So if you look at this, this now is a linear combination of two solutions with arbitrary constants alpha and beta. And this just looks like is equal to 0. And now if I can just say that this one satisfies the Laplace equation, and this one satisfies the Laplace equation. So any linear combination of solutions is also a solution of the Laplace equation. So I gotta pick the expansion coefficients, which are called Cn in our case, to satisfy the boundary conditions. So now how do I do that? That's the next question. So, boundary condition number 3. That's the final one. And it says that at x equals 0, the potential is equal to a given function, v naught of y. And now I can write down my solution, which is just the sum over there, to match this solution here. So we get so our sum now has to be equal to this function here. And that's the given function on this plane, which we enforce. And now, of course, this starts to look like a Fourier series, and it is. So we're going to figure out what's Cn. And when we figure out Cn, we're going to know the solution. And we're going to use Fourier's trick, which is just the following. We just multiply by sine of Km on each side, and then we integrate. Which we love to do. So let's see, we end up with one integral for each Cn. I'll show you. And now the constant is just multiplicative, right? So I put it outside the integral sign. This is the left-hand side, and it's pretty big and nasty. So on the right-hand side, slightly better. No, let's see. I'll just look at this one for now. So this is the left-hand side of this equation, and I'm doing this. Yeah, I'm just going to calculate this integral first. And now, if you look at this, you see that this is equal to the following. Let's see. Yeah, so this is very easy actually. Right. Okay, so for each of these terms, I integrate them, and the answer is as following. It's Cn, which is just a constant, a over 2, which is then the average of, no, let's see. Never mind, that's the width, right? Half width. And this now is delta nm, that's the Kronecker delta again. So it's, if n is equal to m, this one is equal to 1, and otherwise it's 0. So the sum is now very, very easy. Because only one term survives. And that's Cm. And this is, of course, the point of Fourier trick, or the Fourier trick, that these functions are orthogonal. So most of the integrals are actually 0, or all but 1. And then I end up with a constant which I'm interested in. And there's one constant for each value of m, which was the sine function I multiplied with. Any questions on Fourier's trick and that stuff? Okay. So now let's see. And if I look on the, this was the right-hand side, and this now, if I do the same thing on the left-hand side, this is what I get. And this is, of course, equal to the left-hand side. So by Fourier's trick, I got an integral for each c. So all I have to do now is to solve the integral v0 to y sine km y dy on the interval 0 to a, and I can find the expansion coefficient Cm. So of course, I'll move this over here. So now you have an explicit formula for Cm. And now with these Cm, we have that the solution looks like this. Like we wrote down before. So now I can calculate for any v0 of y. I can calculate the coefficient Cm, and I know the solution for our geometry. So as an example, I'm going to do this for v0 of y equal to a constant. So let's start over here again after the break.